There's a photo up on the board right now. What is this? What's going on in this? Yes, you're exactly right. This is jets and a condensation trail that follows these jets. Sometimes we call the condensation trail a contrail, condensation or contrail. Somebody said jets. That means we know that there are two of them, right? How do you know there's two of them? Because there's two trails, right? Two lines. What else do you know about these two jets that pass by at some point? What's one of Aiden? Yes? Yeah, one of them went by more recently than the other one. Which one went by more recently? Let's name them, number one and number two. Number one went by more recently because the condensation, it's actually a cloud that follows it. When you see this up in the sky after a jet's gone by, it's not exhaust from the jet, it's a cloud that follows it. It's condensation. It's mostly water vapor that's condensed into forming a cloud. You can see that number one isn't spread out as much, so it looks like it's passed by more recently than number two has. Okay, what else? We have two jets. Number one passed by more recently than number two. Looks like they crossed by at almost right angles to each other. Did they hit each other? No, they didn't, because then you'd see the condensation trail looking completely different than this, right? Do you know which direction they're going in? Number two looks to be going this way because it looks like the condensation or the cloud is spread further apart up here than it is down here. All of this stuff that you guys have told me without me even telling you that it was airplanes. Okay, you guys told me when I first asked you what this is, you guys told me that it was jets, and a condensation trail that follows the jets. And one jet has gone by more recently, and one jet is going in this particular direction, and one jet, looks like one jet has two engines. Maybe the other one does too. It's kind of hard to tell that. All these things that you guys have told me without me framing this question at all I said was, tell me what's going on here. I'm going to tell you something today that on the last day of Physics 30, the last new material day of Physics 30, and quite possibly, given the time of the year, the last new material day of your entire high school career, possibly, I'm going to tell you something. For the last 13 years, very last day of school, you're learning this. For the last 13 years of school, kindergarten through grade 12, your teachers, when they've taught you about the atom, have lied to you. Now we're going to tell you the truth. The atom does consist of three particles: protons, neutrons, and electrons. But we've always said these are fundamental particles, or at least we've inferred that they're fundamental particles. They are not fundamental particles, or at least two of them are not. Electrons are, at least as far as we know, considered to be fundamental particles. Protons and neutrons aren't. They're made up of smaller particles. I'm going to call them, for the time being, subatomic particles. Subatomic particles are my protons, neutrons, and electrons. And then whatever makes up the protons and neutrons, we're going to call our subatomic particles, because they're even smaller than subatomic particles. We'll talk about what those particles are in a few minutes. But what I want to talk about first is how we observe them. And then we'll talk about what we observe. How do we observe these subatomic particles? Well, we've got to find out what's inside them by breaking them apart. If you have, let's say you've got two cars moving in a parking lot at 7 kilometers per hour, they hit each other. Those two cars hitting each other may cause dents in each other. The fenders may dent, the door may dent, whatever. But you're not going to break apart this car because they're moving very, very slow. There's welds in the car, there's bolts in the car, there's screws in the car that are not going to be broken by a collision, a 14 kilometer per hour collision. We would need, if we wanted to break this car apart, or if this car was to be broken apart so that we could see what was inside, see what it was made of, we would need a collision at a high speed. If you have two cars moving at 110 kilometers per hour and they collide head on, then pieces of the car go everywhere. And it's easy for us to see what makes up the car, the composition of the car, all these different pieces that make up the car. Well, we do the same thing with subatomic particles. Let's say we want to find out what makes up a proton. Let's get a proton moving really, really, really fast. Not like, 1,000 kilometers per hour, but like 2.999 times 10 to the 8 meters per second. 99.99% of the speed of light. Let's get them going ridiculously fast, and then let's smash them into other protons, and then let's see what comes out of it after this collision. See what makes up this proton. But remember that as we do that, as we overcome these forces that keep the protons together, and these little subatomic particles come out of it, we can't see these subatomic particles. They're too small. Like, we can't even see protons, let alone the things that make up protons. So we have to have an indirect way of observing what comes out of them, just like we have an indirect way of observing these airplanes. You're able to determine or deduce some of the properties of these airplanes without actually seeing the airplanes. We're going to do something similar to deduce the properties of these subatomic particles without actually seeing these subatomic particles. So we smash them together. These subatomic particles come out of it because we've broken the attractive bonds in the nucleus with these crazy high energies. And then we try to see indirectly what made up the proton, what came out of this collision. There's two ways that we're going to look at that will allow us to see indirectly these subatomic particles that come as a result of smashing these protons together. One is called the cloud chamber. Okay, fundamentally, remember this. Cloud chambers form clouds. Cloud chambers form clouds. The other one is called the bubble chamber. Bubble chambers form bubbles. The cloud chamber consists of air. This air is supersaturated with water or alcohol. It's ready to rain water, or it's ready to rain alcohol, but it's not yet. It's still a gas. Now, when we smash these particles together, these protons together, these subatomic particles that come out of it, they're charged. So these charged particles that are produced from the collision, these subatomic particles, as I call them, they ionize molecules along the path. So these, whatever they are, these subatomic particles are moving along there in this dust-free air that's supersaturated with water or alcohol, and they cause they ionize molecules of this water slash alcohol slash air mixture, and that causes this gas, this vapor, to condense into a liquid. That's a cloud. Right? When condensation occurs, we get a cloud. So now what we do is follow the cloud path behind this subatomic particle to deduce properties of the subatomic particle, just like we follow the cloud path behind the airplane to deduce properties of the airplane. We can't see the airplane, but we know stuff about the airplane. We can't see the subatomic particle, but we know stuff about it because of the path, because we can follow its path based on the path of these clouds that are formed behind it. Now, the other one, the bubble chamber, is similar yet different. Instead of having a gas, this dust-free air that's ready to become a liquid, we have this liquid that's ready to become a gas. This gas that's been liquefied lowers the boiling point. What we want to do is when we fire these protons at each other, they essentially explode, and the little subatomic particles come out of it. They ionize the material again, and that causes, instead of causing the gas to become a liquid, it causes this liquid that's barely a liquid, right? This gas was barely a gas. All we had to do is ionize some molecules in there, and that gas became a liquid. Here, we've got a liquid that's barely a liquid. It's almost a gas. All we got to do is have these subatomic particles going through their ionized material, and that's going to cause this liquid to become a gas. So what do we see? Well, instead of having clouds following the path of these subatomic particles, now we have bubbles, because the liquid boils. So bubbles follow it. Instead of following the clouds behind the airplanes or the clouds behind the subatomic particles, now we're following bubbles. If this is the analogy for the cloud chamber, then the analogy for the bubble chamber would be your little brother or sister with one of those lawnmowers that blows out bubbles. You know what I'm talking about? Okay? Your little brother or sister pushing the lawnmower that blows out the soap bubbles. Okay, even if you can't see your little brother or sister, you can at least deduce something about their path based on where you see the bubbles. We're following the bubbles as opposed to following the clouds. Now, what do we do? Like, how do we figure out anything from these clouds and bubbles? Well, there's all kinds of things we can do. We can observe their path. We can introduce magnetic fields. We can introduce electric fields. We can measure radii. We can measure charge to mass ratios, try to measure charge, try to measure mass, all kinds of different things, and eventually maybe deduce some properties that we don't already know. Does that make sense? All right, what exactly do we get out of this now? Like, once we do all this, once we fire these protons or whatever into each other and get these sub-subatomic particles out, and once we measure the properties, and once we've established all of these things, what is it exactly that we see? What is it exactly that we get out of it? What are these sub-subatomic particles made up of? What do they consist of? This is the table that you see in the notes that I photocopied. The majority of this table you do not need to remember. The reason that I'm giving you all of the information on here is for perspective. Okay, I don't believe in giving you the 3 or 4 little bits of information that you need to know. I don't believe in giving you those in a vacuum. Okay, you'll see them, you might even remember them, but it's not going to make any sense to you. Even if you answer a question on a test correctly, it's still not going to make any sense to you. So I'm giving you a bit of a bigger picture so that it makes sense. And then I'm going to say, this is what you need to remember. Does that make sense? So what I circle on this table in purple, is what you need to remember. Everything else is big picture stuff, so that you just have a kind of a grasp as to where things fall. I call this the Subatomic Zoo. It's like a zoo filled with all these different animals, and some of these animals are in their own little corner over there, and some of them are in their own little corner over there. We're going to focus. We got to look at the zoo. We got to look at the whole zoo, but we're going to focus on just a few animals in the zoo here. All particles can be broken down into one of 2 categories. First one's called fermions. Second one's called bosons. It's fermions that we're going to focus on. But I'm briefly going to mention bosons. Bosons are force carriers. They're glue. They hold things together. Examples of bosons might be a photon. We've seen photons before. We know what a photon is, right? Well, now we know how to classify that particle. Remember, we called it a wave and a particle? It's a particle, a fundamental particle that we call a boson. There's gluons, there's gravitons that are thought to be responsible for gravity. There's one that was just discovered within the last couple of years that you may remember hearing about. It was theorized, hypothesized for decades, but it's only been the last couple of years that we've actually experimentally observed it for the first time. You ever heard of the Higgs Boson? Higgs Boson that was decades ago theorized to be responsible for mass. This is what causes mass. And now we've seen it. As of a couple of years ago now, we've seen it. So all these different examples of bosons, but we don't need to remember these. Okay, just understand that these are particles that fit in the same zoo as these other particles, but they're off in another corner that we're not going to explore today. So let's go back to the fermions. This is the section of the zoo that we care about. Specifically, there are 2 categories of fermions as well. Take a look at your data sheet for a second. Bottom right-hand corner, you're going to see some data for electrons, positrons. What's the heading for that? What does it say right above that data? First generation fermions. Okay, these are fermions. Fermions can be broken into these 2 categories, leptons and hadrons. The first category is the lepton. The lepton is a particle that is not mediated by the strong nuclear force. You guys remember that strong nuclear force? That force that acts between all of the things inside the nucleus, the proton, the neutron, the proton, the neutron. Attractive force. These leptons are not affected by the strong nuclear force. They're not mediated by the strong nuclear force. And they are, as far as we know, fundamental particles. An example of a lepton would be an electron. An electron is a lepton. It doesn't get any smaller than an electron. Now, along with the electron, we have we call it the electron neutrino. When we talk about beta decay, beta negative, beta positive decay, and we're talking about neutrinos and antineutrinos, those are electron neutrinos. We just call them neutrinos because it's the only kind of neutrino that we deal with in Physics 30. There are two other types of neutrinos as well, but we don't deal with them, so we usually just don't put that term electron in front of a neutrino. We see neutrino, we just assume that it's an electron neutrino. There is also a muon. You ever heard of a muon? Anybody ever heard that word before, a muon? There's also the tau. Of course, there's the muon neutrino and the tau neutrino. And in addition to the electron neutrino, the muon neutrino, the tau neutrino, whatever, there's also the antiparticles. So there's the anti-electron, which is known as the positron. There's the electron antineutrino, which is known as the antineutrino, or as we just call it, the antineutrino. So again, what's circled in purple, you need to be familiar with. Leptons, fundamental particles, no strong nuclear force. Electron, and then the neutrino and the antineutrino, and the positron. Now, the other category of particles that we need to be familiar with are hadrons. They are mediated by the strong nuclear force. In other words, that strong nuclear force affects hadrons. You ever heard of the LHC, the Large Hadron Collider? It's a particle accelerator that straddles the border between Switzerland and France, and it's massive. I think it's something like 30 kilometers, something like that, in circumference. They accelerate these large hadrons to really, really high speeds, 99.999% the speed of light, and then they smash into each other and see what comes out of it. What comes out of it? What is it that comes out of it? Quarks and antiquarks. These are the particles that make up hadrons. Now, there's two categories of hadrons as well. There's these baryons and these mesons. We're not going to worry so much about the distinction there. It just is a matter of what makes them up, whether it's three quarks that make them up, or a quark and an antiquark, or whatever. By the way, how long do you think a meson would exist for? Not very long. How come? Right, exactly. We're concerned with these baryons, which are made up of three quarks. An example of a baryon might be a proton. Another example of a baryon would be a neutron. These quarks, by the way, notice not in purple here. These quarks, there are 6 examples of quarks. There's the up quark, and there's the down quark. There's the top quark, and there's the bottom quark. And then there's the charm quark. Man, these keep getting stranger all the time, right? We got up, down, top, bottom. By the way, when I was in high school at your age, there was 6 quarks established, but only 5 of them had been experimentally observed. The top quark hadn't been. We knew that it had to be there, but we hadn't observed it. And since that, long ago, we've observed this top quark. We have the up, down, top, bottom, charm, and what would be stranger than any of these other quark names? What word, what name of a quark, what could possibly be stranger than any of these? Yeah? Nope. That would be stranger, but this is even stranger than sprinkle. This is the strangest word ever. It's called the strange quark, yes. The up, the down, the top, the bottom, the charm, and the strange quark. Good. The up quark has a charge of plus 2/3 of the elementary charge. The down quark has a charge of negative 1/3 of the elementary charge. I'm going to circle this in purple as well. We do need to know this, but the good news is those numbers are on your data sheet, so you don't need to memorize them. You just need to be familiar with those charges. Now, what do you think the charge of of course, if there's quarks, there's also antiquarks. What do you think the charge, without looking on your data sheet, it's there, but without looking at it, what would the charge of an anti-up, anti-quark be? Which, by the way, is not a down quark. Anti-up, anti-down, anti-up, anti-quark is not a down quark. Anti-up, anti-quark. Gets confusing, eh? That's just the antiparticle of an up quark. What do you think the charge of it would be, Aiden? Yep. Not an integer, but negative 2/3, right? If the up quark is 2/3, then the anti-up anti-quark would be negative 2/3. And if the down quark is negative 1/3, then the anti-down anti-quark would be positive 1/3, right? But don't worry about that. Don't panic about those numbers because, as I say, they're on your data sheet if you ever need them. So what are you going to take away from this, guys? There's this big, massive puzzle here. We need to just fill in a few pieces, but at least now we see where these pieces fit in the puzzle. We need to know that, as far as we're concerned, there are two types of particles. There's the leptons and the hadrons. The leptons not mediated by the strong nuclear force. Hadrons are mediated by the strong nuclear force. Leptons are fundamental. Electrons, neutrinos, positrons, antineutrinos. The hadrons are made up of quarks. Protons are examples of hadrons that are made up of quarks. Neutrons are as well. Hey, before I flip the page here to the last page of Physics 30, knowing that a proton is made up of 3 quarks, and knowing that an up quark is 2/3 and a down quark is negative 1/3, what do you think the composition of a proton is? The quark composition is. If we go up, down, down, look at what that would be. Up would be 2/3, down would be negative 1/3, down would be negative 1/3, 2/3, negative 1/3 gives me 0. That would be that'd be a neutron. Does that make sense? What would a proton be then? Knowing that it has to be 3 quarks, not antiquarks, because if it was antiquarks, then it wouldn't be matter, right? UUD, let's try that one. Up is 2/3, down is negative 1/3. No, what did you say? UD? You said UUD, didn't you? Yeah. We know it's not UDD because we just established that it wasn't. Up is 2/3, up is 2/3, down is negative 1/3. What does that add up to give me? That adds up to give me 1 elementary charge, which is the charge of the proton, right? Yep. Yeah. In essence, yes. But at a certain level, it's still good, right? But it's just when we're talking about subatomic particles on a different level, it's not. But on the level at which we would normally work, yes, it still works for us. Okay, I want to flip the page here and just real briefly summarize beta decay now. Why are we doing beta decay? We finished beta decay last week. Well, I want to do it in terms of our quark composition. Remember beta negative decay? Beta negative decay occurs when you have too many neutrons, and a neutron changes into a proton and an electron. And what else? An antineutrino? Right, beta negative, the antineutrino here. So let's say a neutron consists of up, down, down. A proton consists of up, up, down, plus your beta particle, plus your antineutrino. Now, this doesn't fully explain by any means how beta negative decay occurs, but at least it shows you that, okay, a neutron and proton are not fundamental. So at least it opens up the possibility of something shifting around and making something else. Whereas 2 weeks ago when we looked at this for the first time, you're like, what, a neutron just changes? into a proton. Okay, I'm still not really describing the mechanism, but at least you can see that maybe there can be some rearranging of some things going on there. Beta positive decay. This is when you had too many protons changed into a neutron and a what? And a positron. Remember, positron is E plus 1, plus what else? Plus the neutrino. Proton is up, up, down. Although you don't need to remember that, right? You can figure it out, like you guys did a minute ago. Goes into a neutron, up, down, down. Now, really and truly, it's kind of a two-step problem here. This decays. It's an up, up, down, goes to an up, down, down, and then something that we call a virtual particle, which in turn decays into a positron and a neutrino. But as far as we're concerned, it's good enough to say that the up, up, down decays into an up, down, down, a positron, and a neutrino, even though there is a couple of steps there, and we're only describing one. We're kind of combining it into one step.